You might have heard that the Milky Way galaxy will collide with the neighboring Andromeda galaxy in the next 4 to 5 billion years, completely merging with it in the next 6 billion years. But that won't be the first collision of our galaxy with another. The Milky Way is the second largest member of the local group, comprising of at least 80 known galaxies. Satellite galaxies orbiting the giant ones end up being torn apart and ultimately merging with the massive galaxies. The Milky Way is already merging with several satellite galaxies, but one of the most prominent mergers is with the Sagittarius dwarf galaxy. Astronomers have found evidence that Sagittarius has already passed through the Milky Way thrice in the past 6 billion years, which might be the reason behind our existence. But how did scientists make this intriguing discovery? How do they know the number of times the Sagittarius dwarf galaxy passed through the Milky Way? Finally, and most importantly, why is Sagittarius considered the reason behind the existence of life on Earth? Whenever two galaxies interact, they may or may not lead to a merger. For example, consider the Tadpole Galaxy, lying 420 million light-years away in the constellation of Draco. The most striking feature of this galaxy is a star trail extending 280,000 light-years. Astronomers have found evidence that about 100 million years ago, a compact intruder galaxy crossed in front of the Tadpole Galaxy from left to right from Earth's perspective. During this close encounter, tidal forces drew out the spiral galaxy stars, gases, and dust, forming the conspicuous trail. Small satellite galaxies and star clusters orbiting the Milky Way are often torn apart by their gravitational potential, leaving behind trails of stars stretched out across the sky. These stellar streams contain information about the history of their parent object. They can be studied to learn about the evolution of the Milky Way in an approach referred to as galactic archeology. And here's the trick to finding what happened in the Milky Way billions of years ago. The most important tool to study stellar astrophysics is the Hertzsprung-Russell diagram, a scatter graph between the star's luminosity and its surface temperature. One can plot every star in the universe on this diagram. If you don't know about the HR diagram in astrophysics, here's a quick overview. The x-axis of this graph represents the star's surface temperature, which decreases along the axis. The y-axis represents the star's brightness or luminosity, which increases all the way up. 4 main groups of stars can be plotted on the HR diagram. The first is the main sequence that includes all the stars currently converting hydrogen into helium in their core. The Sun lies around the middle of the diagram in the main sequence phase. The next group is that of the giant stars that form once a star exits the main sequence and turns towards the right side of the diagram. Then we have the supergiant stars with higher luminosity and the white dwarf stars and neutron stars with low luminosity but high surface temperature. Stars that form simultaneously in the same environment will have the same composition and age, but will also have a wide range of masses that will trace out a distinctive curve on Hertzsprung-Russell diagram. Consider this diagram of the stellar population as an example. Different colored lines illustrate how different populations of stars evolve. The stars formed within the last 25 million years trace an almost straight line, meaning that none of them have exited the main sequence. But the stars formed in the past 10 billion years show a bump and trace a different curve. This illustrates that most of these stars are old and have turned into red giants or hypergiants and moved towards the right side of the HR diagram. After analyzing the star formation history of the Sagittarius dwarf galaxy and studying the stars in the Sagittarius stream, astronomers concluded that the elliptical loop-shaped galaxy fell into the Milky Way 3 times. First about 5 or 6 billion years ago, then about 2 billion years ago, and finally 1 billion years ago. Looking into the Gaia data, astronomers found 3 periods of increased star formation that peaked 5.7 billion years ago, 1.9 billion years ago, and 1 billion years ago, corresponding with the time when Sagittarius is believed to have passed through the disk of the Milky Way. So after an initial violent epoch of star formation, the Milky Way finally attained equilibrium, a balanced state with a steady star formation rate. But then, Sagittarius fell in and disrupted this equilibrium, causing all the previously still gas and dust inside the larger galaxy to slosh around like ripples on the water. In some areas of the Milky Way, these ripples would lead to higher dust and gas concentrations, while emptying others. The high density of material in those areas would then trigger the formation of new stars. An important part of the Milky Way's stellar mass was formed due to the interactions with Sagittarius and wouldn't exist otherwise. It's also possible that even the Sun and its planets would not have existed if the Sagittarius dwarf had not gotten trapped by the gravitational pull of the Milky Way and eventually smashed through its disk. The Sun formed at the time when stars were forming in the Milky Way because of the first Sagittarius passage. Another team of astronomers also analyzed the star formation history of the Sagittarius stream. They were especially interested in a region where the stream is split into 2, a brighter half and a fainter half. They wanted to know if both the streams came from the Sagittarius dwarf galaxy, and if yes, what caused the difference in their brightness. They discovered that the stars from bright and faint regions follow a tight relation between age and composition, meaning that at any given time, the stars being formed had a similar composition and formed in a homogeneous environment. They also found that this relationship is similar to that of stellar clusters, known to belong to the Sagittarius dwarf, confirming that both the bright and faint parts of the stream were stripped from the galaxy. The ages of stars in the 2 parts of the stream span about 8 billion years and then have a cutoff that indicates that star formation in the Sagittarius dwarf stopped about 5 billion years ago. This sudden halt of star formation was probably caused by the Sagittarius dwarf being torn apart. The difference in their brightness is due to the different periods in which they were stripped. Observations of the stars in the Sagittarius stream could provide clues to the history of star formation and the destruction of the Sagittarius dwarf galaxy. And these studies were made possible by data from the Gaia spacecraft that is silently revolutionizing astronomy. And the recent Gaia Data Release 3 is a treasure trove that will change our understanding of the universe. This concludes another episode of the Sunday Discovery series. So, if you enjoyed it, make sure to like it, subscribe to our channel, and press the bell icon for more.